In this session, we're going to look at the Markov and Chebyshev inequalities. You should be aware that these are somewhat crude inequalities because they don't rely upon the underlying nature of the random variable. But they can be, they're useful in other results. And we'll use them to analyze results of a voter polling survey, and so you'll see how they might have some practical application as well as theoretical ones. Okay, so the Markov inequality. Okay. So if you have a non-negative random variable, sometimes it can take values greater than the expectation. What's the bound on the probability of an individual distribution taking a value greater than the expectation? Okay. So here's the statement. Let x be a random variable that only takes non-negative values. Okay. Let a be a positive real number. Then the possibility that x is greater than or equal to a is less than or equal to the expectation of x divided by a. So what's the probability that x is greater than or equal to, for example, 10 times the expectation? Markov says that that's less than or equal to 1/10. Okay, and that's, again, it's a remarkable result because it doesn't rely at all on the nature of the random variable. Right? This is just any random variable that is not taking negative values. Okay, so the proof is also surprisingly simple. The probability that x is greater than or equal to a, that's the you integrate the PDF from a to infinity. If you multiply by a inside the integral, a is a constant, so I can just divide by a outside the integral. And so I haven't changed the integral by doing this. And now a is positive, right? And x is greater than or equal to a, right? We're going from a to infinity, so x is greater than or equal to a. So I can say that this integral here is the integral of a f of a times the PDF. Those values are less than or equal to x times the PDF. Okay, which means that this integral on the second line is less than or equal to this integral on the third line. Well, what's the integral from, what would be the integral from x equals 0 to infinity? Right? So this is less than or equal to, this integral is less than or equal to the integral from 0 to infinity of x times the PDF. Right now, x doesn't take any non-negative values, so that's actually the integral. That would be the integral from minus infinity to infinity. So this is less than or equal to the expectation of x divided by a. Okay. All right. So a corollary is that as the probability for x, a non-negative random variable with a finite expectation, and a being a positive real, then probability that x is greater than or equal to a times the expectation is less than or equal to 1 over a. Okay. All right. So here's an example. If we're concerned with income distributions, we don't know how the incomes are distributed. So I don't have the underlying nature of the distribution to work with, but then Markov doesn't depend upon that. And incomes are non-zero. Okay, so if we look at the probability of a random person being chosen, having an income more than 5 times the expectation, here the expectation would be probably estimated by a sample mean. The probability of any random person being chosen having an income more than 5 times the expectation is less than 1/5. Okay. Now we're going to do a problem with a voting survey or a voting intention survey. And we're going to see what Markov can tell us about that. And then once we've done Chebyshev, we'll see what Chebyshev can tell us about this. Okay, so there's a total of small n voters in law. We want to estimate how many may intend to vote for the Baba Rhinoceros Party. You can't ask all of them. That's essentially doing the election, right? But we're going to do a survey, and we're going to make an estimate of the fraction p that will vote for the Baba Rhinoceros candidate. Okay. So now the thing is, I can get an estimate. How good is that estimate? Right? There's some actual fraction p of voters, and of all the voters who intend to vote for Baba Rhinoceros Party. Now, I take a sample capital N of the total number n. Okay, and we'll suppose that their voting preferences are independent. So you don't just like say, I'm going to take a sample of 100 and I'll take 10 families with 10 people each and ask them, because voting within families may not be independent, for example. Okay, so suppose that B out of the N, capital N, say that they will vote Baba Rhinoceros. So we can estimate that P, I don't know what P actually is, but my estimate for P is B over N. Now the question is, how bad can this estimate be? Okay. How far off can it be from the actual value P? Okay, so now we translate this into our probability language. So let's define random variables xi. I goes from 1 to capital N. Okay, so we asked the opinion of people that we've labeled, person 1, person 2, person 3, up to person N. So the random variable xi takes the value 1 if the ith person says they're going to vote Baba Rhinoceros. And it takes the value 0 if the person does not want to vote for Baba Rhinoceros. Okay. P is the fraction of voters intending to vote Baba Rhinoceros. So the probability that someone says that if the ith person says that they will vote Baba Rhinoceros, and so the probability that random variable xi equals 1 is equal to P. And the probability that xi equals 0, that is that the ith person says that they will not vote Baba Rhinoceros, that's equal to 1 minus P. Okay. Now, what's the expectation of each xi? Well, it's equal to the sum over the allowed values that xi can take times the probability of xi. Well, xi can take a value 0, will not vote Baba Rhinoceros, times the probability of not voting Baba Rhinoceros, 1 minus P, plus 1, that means they want to vote Baba Rhinoceros, times the probability that any random person will vote for Rhinoceros is P. And so the expectation of xi is P. Okay. Now, B, that's the number of people who say that they're voting Barbara Rhinoceros. That's just the sum of xi, I equals 1 to n. Then the expectation of B is equal to the sum of the expectations of the ni from I equals 1 to n. Now, each one of these expectation of xi's is P, and you have n of them. So this sum works out to np. So the expectation of B is equal to np. Now we ask, what's the probability that the B we get is more than twice the expected value of B equals np? Okay. This is the actual number of people who will be voting. Oh, sorry. This is the expected number of people who would be voting for. So the probability of B is greater than, and this P is unknown, right? The probability of B is greater than twice the expectation of B, according to Markov inequality, is less than or equal to 1/2. Okay. So the probability that we overestimated the popularity of the Barbara Rhinoceros candidate by doing this survey, that we overestimated by a factor of 2, that's less than or equal to 1/2. Okay. Okay. But the fact that B is greater than or equal to 2x, so twice exponent, the fact that B is equal to twice x, twice the expectation of x, implies that B is equal to greater than or equal to twice np, which implies that if we do a little algebra, B over n is greater than or equal to twice p. Okay, so once again, if we estimate p by B over n, the probability that we have overestimated by twice or more is less than 1/2. Okay. All right. It didn't really matter what n was in this case. And so Markov is assuring us that if we make our estimate by this, like this, the most that we're overestimating our support for is a factor of 2. Okay. So we can actually do better than that, and that's by going to the Chebyshev inequality. And once we have the Chebyshev inequality, then we'll go back to this voting survey example, and we get a somewhat better bound for this. Okay. So the Chebyshev inequality. If x is a random variable with expectation mu and variance sigma squared, then for any a greater than 0, we have that the probability that x differs from its expectation by more than a sigmas is less than or equal to 1 over a squared. Okay. So, for example, let's say x is a random variable. Then what happens when we consider 2 sigmas? What's the probability that x takes values that are more than 2 sigmas away from its expectation? Well, this says 1 over 2 squared. So the probability of x taking a value more than 2 standard deviations away from its expectation is less than or equal to 1 over 4. Okay, so the proof is in the lecture slides kind of drones on for a bit, and I'm more interested in the applications. So in this course anyways. So once again, eventually we will get that the probability that X differs from its expectation by more than A sigmas is less than equal to sigma squared over A squared. Okay, or the probability that X differs from its expectation by more than A sigmas is less than or equal to 1 over A squared. Okay. Now, if we go back to the voting survey problem, right, the XI, the expectation that any particular person will say yes is they're going to vote Bob or Anas versus P, and then you can work out that the variance is P squared times 1 minus P squared, variance of XI. If you've forgotten how to calculate the variance, we need to review that. We do that as an exercise. And then if we're using independence, with B is equal to summation of Xi, then the expectation of B is equal to NP, and the variance is equal to, we can just N squared, P squared, 1 minus P squared. We just get N squared in front of this. Okay, using independence. If it's not independent, this term is more complicated for the variance. Okay. And now, if we use the corollary to Chebyshev, the probability that this B over N is away from its expectation by more than epsilon, that's equal to P squared times 1 minus P squared over epsilon squared. Okay, so once again, these results don't depend upon the underlying distribution. If you know the underlying distribution, you could get tighter bounds on the inequalities. But sometimes we don't even know what the underlying distribution is. But then Chebyshev and Markov can still tell us something.